Okay, good. All right, everybody, take a seat, please. Okay, great. Thanks everybody for being here on time for the Friday morning session. We have several speakers this morning, and our first is Zinger talking about a sea of jellyfish.
So good morning everyone. I'm Zinger from the Hebrew University. I'll be telling you about our jellyfish galaxy Zooniverse project and the results that we got from it. This is work done with the group in Heidelberg, with Annalisa's group in Heidelberg. And let's just jump into the ocean. So first of all, we've been talking all week about jellyfish galaxy, but nobody's actually shown a jellyfish. So I think I'd rectify that. And you know, looking at these pictures, you figure out why they call them jellyfish galaxies. And even in simulations, we get really nice jellyfish galaxies. And as we know, this is all due to ram pressure. I thought I'd show some terrestrial examples of ram pressure just so we could get a feel for how effective this stuff could be. And we decided to study jellyfish galaxies in simulations where you can have a very, very large sample of galaxies to look at. Specifically, you all know this picture, of course. We looked at the TNG50 and TNG100, figuring we'd need the higher resolution in these two boxes to really get the goings-on in jellyfish galaxies. And this gives us a potential pool over several snapshots of order 10 to the 5, maybe even more candidates to look through. And the way we decided to look at jellyfish galaxies is the way that most people look for jellyfish galaxies, just looking at them. And just looking at this picture, it's easy to see why these would be called jellyfish and these would not. So our first project on this subject came out in 2019, led by Kyun Yoon. We looked at about 2,000 galaxies. We did all the visual classification in-house, just 5 of us looking at a bunch of pictures. We ended up with about 800 jellyfish galaxies. It was really cool. This is a nice picture. You can see the bow shocks that are identified around these galaxies. But what would you do when you want to go a bit further and look at about 100,000 galaxies? So rather than destroy your eyesight, you ask for help. And that's what we did. We turned to Zooniverse. We set up a citizen science project. And we asked people, come help us identify jellyfish galaxies from our simulation. And if you don't know this site, it's very, very cool. It's expanded way beyond astronomy and has projects in every sort of discipline you could think of. So to start things off, we had to decide on a satellite sample. So we looked at redshifts going all the way up to redshift 2. So this kind of shows how many objects we have from each snapshot in the simulation we decided to use in TNG50 and TNG100. And one of the things we did in this project is for TNG50, every snapshot from 0.5 to 0 was examined. So we have a continuous classification for galaxies going from 0.5 all the way to redshift 0. So that was very, very helpful, and we'll see the results for that in the 2 papers we'll show at the end. Our stellar mass cut was set by the resolution of the simulation, so that's, you can't get away from that. But we imposed no limit on the halo mass, and this is the mass function for the satellites and for the halo, host halos that we got for these objects. And finally, we demanded that there be some gas. I mean, we didn't want to look at objects which have no gas in them, so that's just a waste of time. So we did have some limit on how much gas. We had to have some gas in the subhalo. And since we're looking at snapshots, we're treating each instance of a galaxy as a separate image to be classified. So many times we'll have the same galaxy being classified over time different. So these things can be. So then we generated about 90,000 images and presented them to the project. They were prepared in a random orientation, and we were showing the density of gas in color bars and the stellar contours to show the body, and that's how you can see, you can compare between the 2 of them. And we finally just asked a very simple question: do you think this galaxy looks like a jellyfish? Of course, we had some explanations, examples, a tutorial, the works, but it boiled down to this very, very simple classification task. We did tell them they were told that volunteers should search for filaments which are emanating from the stellar body, so nothing very, very far away. And the reason I'm saying that these two choices basically set that the focus is on ISM gas being stripped and not CGM gas, for example. If you want to do that, we can do that separate project. But our focus here was on actual ISM gas being stripped because of these two choices mainly. And then we sent it out. We wanted, since we were talking about people who are not necessarily expert or had ever seen a galaxy before, we wanted at least 20 classifications per image. And in the end, about 6,000 volunteers took part and generated roughly 1.8 million classifications for our objects. This is a histogram for the number of classifications per inspector and how many inspectors classified this amount. You can see that a lot of people just dabble, they classify just a few images. The median is around several hundred, the mean is around several hundred galaxies. And you can see that some very, very brave and dedicated souls actually classified over 10,000 images, which is amazing. I salute these people. Speaking to the universe team, it turns out that this is pretty common. About 80% of the work in a project is done by roughly 20% of the volunteers. So this is always the case. But because of that, because we have these several people who become probably very experienced and many people who only classify a few objects and probably don't even 10, that did inform the way that we assessed their classifications, and I'll say a few words about it in a minute. In addition, we also took about 8,000 galaxies and showed two images of them. One of them is random, but the other one was optimized. The velocity vector was in the plane of the image, and that's better to seeing the tails, and that way we could get an idea for what projection effects might do to classifications. And we validated the results by comparing those results to two projects that we did in-house, so comparing and seeing how well they matched up. So to get an idea of how good is this classification. And as I said, since we came up with an adjusted score, we came up with a scheme for weighting the classifications for inspectors based on their inspection history. All the details are in the paper, but the idea is that we did take into account who is more experienced and less experienced in generating that. And this is the final distribution of our scores, and this is in log scale, so you can see that the top end where things are probably jellyfish, it's a very low number. Jellyfish galaxies are rare, especially when you look at them in random orientation. So finally, we had our scores, and we could see that it correlates nicely with the pictures. Indeed, things that get low scores do not look like jellyfish. Things that get high scores do. And our goal in our project was to obtain a highly pure, but not necessarily complete. So we wanted a sample which is jellyfish for sure, even if that means leaving out a few that might get a slightly smaller score. But the thing is that if you want to do a project, you can take our data and you can set your own threshold and decide what you call a jellyfish galaxy. So we chose a threshold of 0.8 in scores, and doing that gave us a sample of 5,000 instances of jellyfish galaxies in our simulation. It's a huge number. And as I said, the full data set is publicly available. I'll throw up a QR code if somebody really wants to go and look. And finally, let's talk some science. So the first paper I'm going to talk about is basically introducing the projects, which is what I did, and showing some demographics, general demographics for jellyfish galaxies. So now with this huge sample, we can actually look at how jellyfish fractions change with redshift, from redshift 2 to the present, how that slices up with stellar mass of the galaxies, with host mass. You can see that jellyfish fractions grow over time as hosts become more massive and more conducive to jellyfish formation. Clusters, which are in red here, you can see go up, and in cluster mass you can get up to 35–40% of the population might be jellyfish. These numbers are lower for lower mass hosts, but even for very low mass hosts like 10 to the 12, 10 to the 11, you still get some jellyfish in these low mass hosts. If you take a closer look at the host mass, so this picture shows us the contours, the blue contours are the jellyfish population. This is in the stellar mass, host mass plane. Red is the non-jellyfish, the general population. And you can see that there's a difference. Jellyfish galaxies prefer more massive hosts. That stands to reason. If you look at the histogram, though, for the host mass, you'll see that, yes, clusters have a lot of jellyfish, but most jellyfish galaxies are found in groups, because there are that many more groups in the universe rather than clusters. Clusters are rare. Even if you stack them full of jellyfish, that's not going to be able to compete with the sheer number of groups that you have in the universe that can host jellyfish galaxies, even if they only have one or two at a given time. So that was pretty cool. And we also found jellyfish galaxies going down to low mass hosts as low as 10 to the 12. We actually found a few at 10 to the 10, and that kind of aroused our suspicion. In the paper, we go into why we don't think that this is actually, these jellyfish actually belong to the host halos. The simulation assigned them, but are probably affected by a more larger host nearby, but that's just kind of in broad strokes. We can also now look at hosts of jellyfish galaxies and ask, how does the host distribution look like? Which host, at which mass host jellyfish galaxies, which do not? And again, we can see that all clusters, basically, everything about 10 to the 14, everything above 10 to the 14 has a jellyfish galaxy, at least one. So if you look at a cluster, you can expect at least one jellyfish galaxy, is usually much more. And if you go down to low hosts, again, you can find, 10 to the 11 point something, still find jellyfish galaxies even in hosts smaller than the Milky Way. If you look at the host mass radial position, then now you can see this is a function of radius in units of R200. Then, as you'd expect, most jellyfish galaxies are found within R200, as one expects. But when you look at it, you see that there's still a sizable population which is found beyond the virial radius. And if you do the number crunching, you can see that you can have as much as 25% of the galaxies may be found beyond the virial radius. And we even looked at which of these were splashbacks, which of these were affected, and it's still a sizable size. It could be first infall jellyfish galaxies found beyond the virial radius, so you can look for those. Another thing we looked at was, now that we had these galaxies, and especially these TNG50 galaxies that you can follow over time, we looked at how these galaxies lost their mass, and this time we actually looked at branches, meaning start with a galaxy at redshift 0, look back to its history, up until redshift 0.5, and see whether at any point it was a jellyfish or not, and then compare the two and see how gas was lost. So this is work led by Eric Rohr, a PhD student at Heidelberg at the Max Planck Institute. This is about 500 branches, and you can see that this is pictures of jellyfish, and you can see that the cold gas emanating from the galaxy is higher metallicity than the surrounding. This is indeed the ISM gas being stripped, as we'd expect. And if you follow one of these galaxies, before infall when it's a central, and you can see how it's losing mass as it goes. After infall, this line shows the mass loss. This line shows, its distance from the center. So this is the first pericentric passage. This is the second pericentric passage. And the black circles show the instances where it was identified as a jellyfish. So you can see right after infall, it starts falling in. You can see where the mass loss occurs. You can follow these things. You can calculate how long does this mass loss phase last. And you can see that this diagram shows that there's a very, very wide distribution. It could be as short as 1 gigayear, and it could last as long as maybe 8 or maybe even more. It could be a very, very long time for a galaxy to lose its gas. But most of the gas loss actually occurs. So this shows you, this color now shows you where the percentage of its initial cold mass loss, where was it lost in terms of time and host-centric distance. And you can see that most of the gas was lost in the first infall within 1 or 2 gigayears, usually lasting no more than 2 gigayears. So most of the gas is lost at the beginning, but star formation in these galaxies, we can see, continues until almost all the gas is used up. We looked at the star formation in jellyfish galaxies, especially this body versus tail. This is led by Yunya, another PhD student. We can see here the map of jellyfish galaxies, and here we're showing the star-forming gas, so you can see they're star-forming in the body, but many of these have star-forming regions in the tails as well. Here, here, here. So we find jellyfish star-forming in the jellyfish tails. This picture shows us kind of the where the star formation in the tails would show up on the star formation stellar mass plot. Many of these galaxies have star formation which is basically 0, below the limit of the simulation, but many of them have low but existent star formation rates. And once again, you can follow the galaxy over time and see where this happened. You can see that in many cases, as there's a pericentric passage, you get this peak of star formation, and this is also where the area is most conducive to forming a jellyfish galaxy. So we see this relation, but not in all cases. Some cases it goes to the pericenter, we don't see a jellyfish at all. Did we miss it, or was there no jellyfish? Did it lose the gas before? You can check these things out. But as a result of that, if you look at a population-wide of jellyfish, you can see that there are indeed many jellyfish galaxies that are well above the star-forming main sequence, but generally they're below. So as a population, jellyfish galaxies are found below the star-forming sequence, at least in our sample. So to summarize, jellyfish galaxies are really cool. I don't think I need to convince you of that. And thanks to Zooniverse and all the volunteers and really wonderful project that's set up by the Zooniverse team, we classify a huge sample of satellite galaxies in our simulation. And this is unprecedented in range of stellar host masses and redshifts. And we have about 5,000 jellyfish galaxies that we're doing exciting science with. The full data set of all the classifications, both the original and the adjusted, are found on the TNG website with the rest of the TNG data. And this is just our take-home messages for the 3 different projects. I'll leave them up here, and questions if anyone has them.
Thank you. That's a really cool sample. Great first results. We'll go with Paolo.
So since you have the full assembly of these halos that host the jellyfish, do you have are you looking into whether the formation of these tails is related to the assembly history, in particular, whether there is any sloshing of the ICM or the intragroup medium, any local effect other than just halo mass?
I think I should have brought like a notebook and write down all these ideas for future projects. We haven't started looking at that yet, but definitely, as I said, we want to look both at jellyfish and also their hosts and see how there's an effect. You can see, we did show that in Eric's paper that the jellyfish galaxies are a source for a lot of cold gas that ends up in the halo itself. So we definitely see an effect of jellyfish galaxies on the halos. We haven't looked at specifically, how the ISM is changed, in all these different aspects, but definitely something we'd want to look at.
Hey, this is awesome. Did you find any systematic differences between TNG 50 and TNG 100 in terms of jellyfish properties, formation, et cetera?
So we found a lot of differences, but these, it's hard to say whether this is because the TNG 50 sample was much larger, or whether the fact that we had much lower mass limit means we could explore smaller masses and then get more jellyfish. And also the images from TNG 50 look better than the images from TNG 100, and we're still set by classification, so it's much easier to see a jellyfish at the resolution of TNG 50 just by the images than TNG 100. So there were a lot of differences. That's why everything is split up, because if you try to plot them together, there's a really mismatch in the size of the sample, but for technical reasons, not actual reasons. So we still have to see whether there's a real difference. And one thing we might do is look at the lower resolution simulations of TNG 50, maybe not classify them again, but just see how different a given galaxy looks, because they're supposed to be the same.
Sorry, just
So
a quick follow-up on that. Is most of the difference between the 50 and 100 sample in the mass range that is technically resolved by 50 but not resolved by 100? Or is there a difference in the higher masses as well that should be resolved in both?
Even if they're resolved in both, the images still look different between. You can tell if an image is TNG 100 and TNG 50, and that might also put in some bias to the identifications.
Hi, thanks. Nice talk. I just wondered, did you check the orientation of jellyfish galaxies according to our scale structure? I wonder if jellyfish galaxies go to halo from field, not from filaments.
We haven't checked that, but we really should.
Hi. When looking at the demographic, you have shown fraction compared to the global population of the halo. Have you just looked when you focus on first infallers, so galaxies before first percent, and how many of them are jellyfish?
We haven't done that cut yet, but we'll definitely try to do that metric as well.
Thank you very much. I have a lot of questions and comments for your notebook in case you're
great.
interested. Regarding the first point here in the star formation, you said that most of the galaxies of the jellyfishes peak the star formation near pericenter. Is there any dependency with the mass or with the mass of the the hosting cluster, because in GASPA we found that for the most massive clusters we have no jellyfishes in the inner region, and we interpreted that as a sign that in the most massive cluster everything is destroyed before they could.
So I can't give you an answer based on data, but we have thought a lot about this issue, and I think there's a difference here, especially in observations between whether you're in the central regions because you're on a pericentric passage, or whether you're in the central regions because you've had enough time to settle there and be there. And if you're there because you've had enough time, then you've lost all your gas. But if you're on a pericentric passage, then you might still have gas and be a jellyfish, and we see many jellyfish actually after a pericentric passage. But then the chances of observing them are much, much smaller because they're just zooming through the center. So in the simulations, we can find them no matter what. But observations, I think it would be very hard to find. It would be rare, not very hard, but rarer to find a galaxy which is just zipping through rather than one who is in the center a lot of time.
But they can survive even in the inner region of the most massive clusters.
On the first pericentric passage, I think yes. I would say.
Okay, let's thank our speaker again.
Thank you very much. Fine, I'm leaving, okay.
Okay, our next speaker is Pavel Jachym, talking about Alma jelly first results.
Thank you. So I want to thank the organizers for this beautiful conference. I tried to Google some, cats hanging out of windows of cars. I didn't find it now, so sorry for that. So I want to present thank you. Maybe the first results is an overstatement, but I want to kind of introduce this project. So it's Alma Jelly, and I'm Pavel Jachym from the Czech Academy of Sciences, and I will show you the rest of the team in another slide. So I have like two introductory slides. So as we already saw and discussed here, the tails of round-pressure strip galaxies are obviously multi-phase systems, and there has been recently a burst of observational evidence of new galaxies, of new tails, of various morphologies and extents and compositions. So I think this is like a golden age of round-pressure strip galaxies. So they obviously the different phases evolve together in the tail, and in some cases they might lead to star formation in the tails. So on the right-hand plot you can see kind of all the phases which were detected in jellyfish tails. So going from cold molecular through H1, warm molecular, warm ionized gas, H-alpha and other optical lines to hot X-rays. And obviously this interaction is a complex hydrodynamics and also the evolution of the gas in the tails. So there are obviously many factors which affect not only how the galaxies are stripped, but also how they evolve and how the stripped gas evolves. So I state some of the parameters here. And lately, I would say like millimeter observations or observations of cold component are one of the newest addition to the picture of jellyfish galaxies. And so far there have been always like mostly individual or small samples observations. So which showed that molecular gas might be an important component. So in some cases there was a lot of molecular gas assuming galactic conversion factor. In some cases even it seemed like the molecular component might be a dominant component of the tail. So there was indeed a time for a larger survey, so I tried it. You don't expect this will work out, but it did. So we got this Alma-Jelly large program in cycle 1. You can see it's over 60 hours with the 12 meter and over 300 hours with a 7 meter array. We didn't ask for the total power time. Maybe we should have, but let's see. So here I state the main goals of the project or of the program. So obviously we wanted to know how frequent is molecular component in jellyfish tails and what is their evolution. Then from studying from other multi-wavelengths data, what is the efficiency of star formation in the tails? Actually, what are the conditions where star formation starts in the tails? Because not always there are stars. What is the evolution? How the cool gas stripped from the galaxies mixes with the surrounding ICM, etc. So the goal was to construct a kind of first systematic sample of molecular tails in jellyfish galaxies on a sub-kiloparsec scale, and there is a lot of complementary multi-wavelengths data to study things I mentioned. So this is a short overview of the basic parameters of the observation. So we observed CO2 to 1 emission at 1 arc-second resolution, which in the cases of those cluster, I will show them, means a sub-kiloparsec scales. It's roughly 500 parsec resolution. Most of the galaxies were done in mosaics because the tails are quite extended. You can see the spectral resolution is slightly over 1 kilometers per second. And I will talk more about that, but basically we say the sample is kind of complete sample for these nearby clusters because we try to cover all galaxies with tails which were known from H-alpha observations. And so the proposal was done in the collaboration with the US, with Ming-san, Scope VI, and Yagi-san in Japan, and there are many people involved. I think we are still in the first stage of kind of processing the data or some first analysis, so mostly the radio team is active, but be aware this is really a work in progress. So quickly, you can see the most of our galaxies. So we have 28 galaxies in these 3 clusters, Coma, Leo, or Able 1367, and Norma. So most of the galaxies are in Coma. I think it's 18 galaxies out of 28. Then in Leo and in Norma, there are only 2. So it's ISO 137, 002, 001, and 002. There is quite a range of stellar masses, other properties. You can see the star formation rates of the galaxies. So in the bottom left plot, I showed our sample and compared it with the 4 galaxies that you observed with ALMA in GASP project. And what we kind of stressed in the proposal is that these galaxies are in different stages of stripping. So I will show it in the next slide. And that also the level of star formation in the tail is, well, there are not so many star formation or not so much star formation in the tails. So this is quickly a view of the H-alpha. So this is how we selected the galaxies. So this is from paper by Yagi in 2010. Those are H-alpha tails in the Coma cluster. And you can already, I think, see the different stages of stripping. Sorry, I will maybe go directly here, but so from kind of early to late. So early means you see some asymmetry in the morphology, but most of things are still happening in the disk. Then in some intermediate state, not so much is happening in the galaxy, but you see an connected H-alpha emission tail to the main galaxy, and let's say in even later state, then probably no star formation or no H-alpha is taking place in the main galaxy. everything was stripped, but you still see some tails, some leftovers of the stripped gas. I will go back to that because I have this for a brief comparison to the GASP sample. So the jelly galaxies are a bit closer, so it makes them easier to observe. I showed the stellar mass range. And what I think is an advantage is that, especially for the comma case, that we have quite a high number of galaxies in one environment. So, obviously you have all the other parameters like different orbits, different inclinations, etc. But still, it's probably easier to kind of deconstruct the orbital history. So they have a lot of them have extended H-alpha tails, and a large fraction of the sample do not have star formation in the tail. So I tried to do quickly this kind of statistics of the detection. So on the top right panel, this is just the distribution of the sample in different stellar mass bins. And so I think we're quite successful. So more than 90% of the galaxies were detected. 80% in the main galaxies, and I would say like 80% of them again in the tails. So on the bottom right plot, if you follow the red dots, so this is where for the 3 mass bins where the main galaxies were detected. So this, then the blue, this is where the tail was detected, and then the dashed lines show where the disk or tail only was detected, and then the green, which overlap with the other blue squares, are like both main galaxy and tail was detected. And we see a variety of morphologies in CO, so I will go to that. So this is like, a snapshot of the results. So on the left, you have one galaxy. We probably have seen it previously because we did study it with Apex, with IRAM, this one. So we knew there was a CO emission in the tail, but now we have a result observation. So this is, so bottom is H-alpha, you can see it. So there is, thank you, there is CO emission up to, let's say, 50 kiloparsec. It's quite interesting. Kinematics looks quite interesting. Then in the middle, this NGC 4858, it was one of the first galaxies that was observed. So this is also quite interesting morphology. The length is not so great, but it's still, we are confident these clumps are real. So those are in comma. Then on top right, this is an example from the LEO cluster. There is a quite extended tail in this 2-mass X telephone number 238 galaxy. And there might be more. This is like higher signal to noise detections, but if you can see this red dot here, this is for sure real, so it's interesting. And I think we saw this galaxy, so this was like first one which we observed some years ago. So we included into our sample because it's still, I think, the richest galaxy, so we re-reduced the data, and you can see it here. So there is like many features in this galaxy. This is the other one galaxy in the Norma cluster, so the bottom ones are in Norma. The ISO 002 is, we observe it edge-on, and it's been stripped edge-on, so we can see the tail in CO. Oh, I'm showing this again because it was, as I said, it was one of the first, and then somebody pointed out it looks like a bunny. So we considered changing our logo to this bunny, but then we realized it was taken already. So. And so we are producing, or in the stage of producing, like atlas of the observed galaxies. So this is one of the early stages galaxy. You can see a lot of things. So this is for these two ISO 137, 01, 02. So you can see the velocity field, velocity dispersion. This is a quick view of okay. So this is again D100, but then like later stages. So especially on the right-hand side, this is another galaxy in the Coma cluster, and you can see the main galaxy is up here. There is no H-alpha in the main galaxy, and then there are these kind of streams. I think there are also these fireballs, UV a continuation of the H-alpha filaments. But you can see these 4 dots. There might be more, but it's really it's low signal to noise. But it's interesting that even in this case, there is molecular gas quite far away from the main galaxy, really in this late stage of evolution. Showing quickly this, it's another case in coma. It's more complicated. You can see the morphology, H-alpha morphology on the left. So clearly there is RAM pressure stripping going from top right, but then what is all the stuff to the bottom right? It's not clear. It's probably a tidal interaction. But again, the kind of reddish orange things are, all these are real. I'm not sure so much about those down here, but there is a lot of stuff. Okay, I wanted to say something quickly about what we did with the data. So I think I was for a long time I was stuck on the imaging of the data because there are basically 2, I think, main difficulties. So there might be a lot of weak signal in the tails, especially. So I think there is still quite a lot of signal which is hidden in the tails. So we try to, or we are trying to integrate. Thank you. Like if we don't see anything, try to follow maybe H-alpha, try to integrate in larger areas and see if CO line can show up. Then we also encountered some like artifacts maybe. It's maybe a little bit visible on the left panel. You see this is NGC 4848 in coma. It's a big bright galaxy and you see all this kind of weaker stuff around the main disk. So we don't think this is real because in H-alpha there is nothing there. So it's probably some cleaning artifacts. We don't know really what to do with that, and it's in more cases. So I think whenever we have a strong disk detection, we have these artifacts surrounding the galaxy. Okay, just one thing. So we decided to use the FANGS pipeline to have a coherent or consistent way of producing the clean images. Maybe like as a first result on the top right, this is the H2 mass fraction for the sample compared to the Santonge sample and vertical sample. What I try to do is different colors are these different stages of stripping. So from green are early through intermediate or advanced down to late phases. You can kind of see there is a trend. So the early stages seem to be above the distribution. So they seem to have more H2 than they should. And then the late, some of them are not detected, are generally below. You can see some funny shapes of the main disks. I have to skip some things and I will finish shortly. Well, you can talk to me. So we have a lot of supporting data. And I think I will leave you with this slide. So this is kind of what we hope we will be able, or people will be able to do with the data set. So to study the star formation efficiency in the tails, because we know star formation efficiency is likely lower in the tails. We want also to search for extended component, because from some, we have for a couple of galaxies, we have single dish, and it seems there is more flux, which was not resolved with ALMA. Obviously, we will have, let's say, more than 100, maybe a couple of hundreds of clouds or clumps identified at the tail, so we can do statistics of their properties and study the correlation of phases, things like that. Thank you very much.
Great, thanks. Okay, I skipped you last time.
Okay, thank you, Pavel, thanks. Well, first to make you feel better, also in the GASP data, ALMA does not recover all the flux if you don't work with it. Okay. You went very briefly through that. You showed the relation between the molecular gas fraction, which is the ratio between molecular gas mass and stellar mass versus stellar mass. And yeah, you put some of the Moretti, so some of the GASP data there. There is also 2023 sample, which is much bigger for GASP. Yeah. And it shows, if I understand, my question is, you're finding the same results, which there is an excess of molecular gas, which is it's a much higher fraction than you expect. And we interpret it as efficient conversion of H1 to H2.
Right.
Is this correct? So you find this? Same
Well,
thing?
so this is initial, or we have to explore it more. But so this is like quickly producing this plot, and you see what you see. So yeah, we see there is more H2, but not in all of them. And there is kind of this trend is kind of visible. So this is kind of reassuring. So maybe or this is what you know, but it's time limited. This more effective transformation of H1 to H2 probably happens in an early stage of stripping or compression, and then when the effect is too strong, then it disappears again. Yes, yeah.
Thanks for the... I think this might be more appropriate for the general discussion at the end, but it occurred to me now, so that's why I'm asking now. I was wondering, based on all these talks, including this very cool project, has there been any study correlating the geometry of the tail to the environment, like the degree of, let's say, the width or the width and the length of the tail relative to the stellar disk? Does that tell us anything about the environment that the galaxy is falling into?
Well, certainly some studies are done, mostly maybe about the direction of the tails. I'm not sure so much about the lengths of the tails. So I think there is space for more analysis in this. Yeah.
Very cool project. Thanks.
Very nice talk, very nice sample. But I was very intrigued by the H-alpha emission that you showed at the very beginning, especially for the late stage galaxies, because they are very far, but I see very clumpy emission. I was wondering if you have studied about the survivability of these objects, if they are dynamically bound, whatever, because they're very far and it's been a while since the stripping. So
yes, so we haven't yet, but this is what we want to do. Yes, in this case it's kind of confusing because the parent galaxy should be that one, not this one. Okay. But I think we detected something here, so it's a bit strange. But yeah, this is what we or somebody needs to do. Yeah.
Thank you.
Thank you.
Okay, let's thank our speaker again.
But I have my time here, so before Bianca tells me I don't speak anymore.
Okay, great. So our next speaker is Benedetta Vulcani, talking about the troubled life of galaxies living in clusters.
So, good morning, everybody. Thank you for being here after the conference dinner. So, we've heard quite a lot in these days about the different mechanisms that affect galaxies in the different environments. But can we actually establish and distinguish between the effects of the different mechanisms and say, yes, surely this galaxy is undergoing this mechanism or these other mechanisms? Obviously, we have heard that there are many cases in which there are multiple mechanisms ongoing, but this is too complicated for now. Let's just focus on the main mechanisms affecting a population of galaxies. So just a brief introduction of galaxy clusters. We know that the galaxy clusters are the most massive relaxed known system in the universe. They are the extreme populations, they are extreme environment, the harshest environment, so we know that they must play a role in galaxy evolution. However, in the local universe, most of the galaxies are passive, red, elliptical, so the question could be, why do we care about local clusters? Everything is already set. But this is actually not true, because clusters are open boxes. There are continuous galaxies that infall into the clusters, and so they affect the general distribution of the population. And when we talk about new infallers, we need to keep in mind that each galaxy can fall into the clusters through a different path. We have some galaxies that fall in as isolated systems. There are some galaxies that fall into clusters, into groups, before falling into clusters. And there can be many combinations of different accretion times, galaxies falling at different epochs. And so in principle, it's very important to keep in mind that the environmental histories of galaxies plays a role. But unfortunately, with current data and We are not able actually to understand very definitely the role of the preprocessing of what happened to the galaxies before entering the clusters and the role of the clusters. And in general, in most of the cases, the strength of the cluster washes out some previous effects. So let's focus on what happens to the galaxies where they fall into the clusters. The fact that there are so many galaxies falling into the clusters entails the clusters grow themselves. When we talk about galaxies evolution in clusters, we need to keep in mind that clusters evolve with time. On one side, clusters grow in mass. From high to low redshift, we have overall a general growth in mass. But also we have a variation in local density. Both from observation and simulation, it has been shown that high redshift clusters were denser in physical space than their local counterparts. So we really need to always remember that clusters change over time. Most of the galaxies that fall into the clusters are typically star-forming galaxies. And then at some point, they quench, they stop forming new stars. Here there is a result from the last STNG simulations that shows the fraction of redshift 0 quench satellites as a function of the time since the last infos. And we see, just focus on the solid lines, that galaxies that just fell into the clusters have a higher probability of being star-forming. The longer the galaxies stay in the cluster, the higher the probability of being quenched. So really, cluster quench galaxies. But why does this happen? This is because there are many different physical mechanisms that happen in clusters. Luckily, we've talked about those quite long, so I don't have to go through all of them. Also, Stephanie already showed this plot showing that the different mechanisms can happen in different environments. So now the question is, what is the evidence of the different physical processes that are at play onto clusters? The first quantity that is typically affected by the cluster population is the gas component. And indeed, also historically, among the first studies, they focus on the H1 deficiency, that is the difference between the gas content a cluster galaxy has and the expected gas content the galaxy should have if it was in the field, keeping the same mass, size, or morphology. And it has been shown that H1 deficient fraction increases with increasing halo mass. More massive clusters have a higher fraction of H1 deficient galaxies, and also that the H1 deficiency increases with the decreasing cluster-centric distance. As we move toward the cluster cores, we have a higher fraction of H1 deficient galaxies. So indeed, galaxies affect the gas content. Unfortunately, it's not always easy to have information on the gas content. So what we can do is studying the star formation rates, and the star formation rate and star formation histories, which are really linked to the amount of gas which is available. Indeed, each process that affects the gas content affects also the star formation rate. So we can consider that in cluster there are two main channels for which galaxies can lose their gas. There is a slow channel, some processes that slowly remove the gas, and a fast channel, so some processes that should very quickly alter the gas content. So let's see what are the pieces of evidence that we have for the two different channels. So when we have a slow gas removal, we typically expect a suppression of the star formation. And this is shown in the star formation rate mass relation. In pink, there are field galaxies. In black, we have cluster galaxies. And we see that while cluster galaxies can be as star-forming and field galaxies, we have a population which is not negligible of galaxies in clusters that are below the star formation rate mass relation. These are galaxies that are transitioning from the main sequence down to the passive cloud, which is down here. And so we can call these galaxies transition galaxies. We can look where these galaxies are in clusters, and we see that they are almost absent in the external regions of the clusters, and they are present very close to the cluster core. So either it's a process that affects galaxies only when they get into the center, or it's a process that takes a lot of time to produce this effect. However, this process should be long enough so that we are able to see these galaxies in this regime. This result is valid not only in the local universe. We can move at intermediate redshift, 0.5, 0.6, and we see again black points here. Galaxy clusters have a reduced star formation rate than their field counterparts. And the same has been shown also in go green up to redshift 1, 1.5. It's always the same thing. We can try to quantify which is the mechanisms. And together with Rose Finger and Greg, last year, we ran some toy models to really understand what is the timescale over which this quenching can happen. So we compare the star formation rate of cluster galaxies to the star formation rate we expect for a star-forming galaxies that at some point enter the clusters, and then after some delay time, it quenches. And so we then compare the star formation rate that we measure and the one we expect, and we run some statistical tests. So the allowed models are either very short time, very long time delay time, and very short tau, so very short declining phase, or very short delay time and very long tau. In the first case, run pressure stripping is the most favored processes in this process. In the second case is starvation. However, if we look at the colors and at the ages of galaxies on the star formation rate mass relation, we see that there is really a continuous population, and this suggests more that starvation should be favored. However, this is just a statistical analysis all over many, many galaxies, but can we actually see starvation on act? Can we detect galaxies that are really the remnants of a starvation effect? This is possible thanks especially to soft data. We can really study where the star formation has been suppressed in galaxies. And this is an example that comes from GASP that, as we already heard, give us many examples of galaxies undergoing the different mechanisms, and this is just one example. This is a passive galaxy. This galaxy already is on the passive clouds. It's not a transition galaxy, but we see, and indeed we see no emission lines, and here we have the stellar kinematics that tells us that the galaxy rotates regularly. There is no a clear signal of, for example, of a merger. And here we have 3 ages of star formation history, and we just see here the extent of the star formation history. And at all epochs, the extent of the star formation rate was very similar. So this suggests that actually the galaxy suppressed its star formation in a similar way at all distances. So starvation really reduced the gas at all distances. And in general, in the remainder of the talk, when you see this vertical line, it means that it's GASP data and showing spatially resolved data. So what are other consequences of starvation? There are at least 2 clear signatures of starvation. On one side, if we look at the mass metallicity relation for galaxies in cluster and in the field, we see the cluster galaxies have a higher metallicity than field galaxies. And this is because starvation prevents galaxies from accreting new low metallicity gas, and so they just use the gas that they have. And on the other hand, starvation is expected not to change the morphology. And so galaxies can quench, become red, but maintaining their morphology. So in clusters, we have an excess of red spirals with respect to the field galaxies. So this is just the first mechanisms, the first way for galaxies to get rid of their star formation. But then we have also another channel that is very fast. And when we have fast truncation of star formation, we expect K+A post-starburst signatures. This is a clear example of a post-starburst galaxy where we have no emission lines and strong Balmer lines. And many models and many studies showed that this is indicative of a suppression of star formation that happened on very short time scale, less than 1 gigayear. Post-starburst galaxies are ubiquitous in the universe. We find them both in the field and in clusters. But if we study the fraction of post-starburst galaxies as a function of halo mass, we see that the fraction is higher in clusters. So the clusters are really a place where it's easy to form post-starburst galaxies. This is true both in the local universe and at high redshift. And in this paper by Adam Mazin, also it was shown that post-starburst galaxies are preferentially found close to the cluster core and at lower masses. We have already heard about post-starburst galaxies, and in general, we think that K+A features are due to different mechanisms in the different environment. In the field, they are merely related to mergers or AGN, while in clusters, run pressure stripping should be responsible. But is this true? We can look at this using spatially resolved data. So here we have again a GASP example in which we selected galaxies that were post-starburst based on the fiber spectrum. And here we have the integrated spectrum using the Muse data, and we see that really there are no emission lines. These galaxies are really post-starburst throughout their disks. Here we have the star formation histories. Here is the youngest age, and we see that there is no signal. These galaxies are passive. And then but then in the second age beams, around 1 gigayear ago, we see that there was star formation. So really the quenching happened very quickly. And another clear signature, especially in this case, is we have an outside-in quenching. Run pressure stripping removes the gas from outside in, and so we really see how the external regions of the galaxies get quenched first than the core. This, though, is the final stage of RAM pressure stripping. But what happens to RAM pressure stripping when it acts on galaxies? There are three main three main points that I want you to remember. Here is again a star formation history of a GASP galaxy. One thing that we see is that on the disk, even though the galaxies still start forming, we see some regions that have post-starbust signatures. So we really see a sign that the gas is being stripped on this side more than on this side. So we really see RAM pressure stripping at play. The other important thing is that on the other side, we see long ionized tails. RAM pressure stripping removes the gas. There are new stars formed in situ, and so we see these nice tails of jellyfish galaxies. And the final thing is that RAM pressure stripping can enhance star formation in the disk. Here again, you can see the star formation history. You see in the center that the galaxy was reducing its star formation rate, and then there is a sudden burst. So there is an enhancement. And this is, in general, these results are valid in the local universe, but also at least up to redshift 0.5. We know very little above. To summarize this better, we can look at the star formation rate mass relation of jellyfish galaxies with respect to the control sample, of undisturbed galaxies in the field and in the cluster, both in the local universe and at redshift 0.4. And in both cases, black points are undisturbed galaxies, colored points are RAM pressure stripped galaxies. And in both cases, we see an enhancement in star formation rates in the disk of RAM pressure stripped galaxies. So this is again a suggestion that RAM pressure stripping can enhance the star formation in the disk before leading to quenching. And we see similar things, Stephanie already mentioned this, also on local scale. We really see a local enhancement in each region of the galaxies. These star formation rates are computed from H-alpha emission, and we need, though, to keep in mind that this could be also some lower limit, because RAM pressure stripping also increases the dust content. And just an example, just because I have to cite JWST, we observed Abel 2744 and its jellyfish galaxies with NIRCam, and we found that jellyfish galaxies, but also some other galaxies in the field actually, have an extreme F200 minus F44 colors. And here you see there's the maps of the colors. And this excess is both in the core of the galaxy, but also up to the tails. Looking at the spectra of this galaxy, we see that there is a strong PIH in emission, and this PIH is typically associated to dust-obscured star formation. So actually, we think that these galaxies have a higher star formation rate than what measured from H-alpha. So the excess could be even higher. So we talk about slow and fast channel, but can we understand which is the major mechanisms in the local universe? Here we have the fraction of galaxies that are in transition in black and the fraction of galaxies that are post-starbust in green. And this is done in a stellar mass bin as a function of cluster-centric distance. And we see, in general, that the fraction coincides very well, except in the core, let's say, where actually we don't have enough post-starbust galaxies, because by the time the galaxies get into the cluster core, they already became passive. They lost the post-starbust signatures. Fractions are similar. However, the visibility phase is very different. Transition galaxies most likely are visible from 2 to 5 gigayears. Post-starbust signatures are visible for 1 gigayear, so we can conclude that post-starbust galaxies contribute more than transition galaxies. So RAM pressure stripping is the main channel in the local universe to quench galaxies. And this has been also discussed in another paper that we did in GASP last year, where we measured the visibility phase of optical tails in cluster galaxies, and we really see that each galaxies in cluster most likely undergo a stripping event which is visible at optical wavelengths in their life. So RAM pressure stripping in the local universe is very important. But yet we still don't know what's going on at higher redshift. So let's just focus a little bit on high redshift galaxies. So in general, we know that as we move from low to high redshift in cluster, the cluster were more star forming, both in terms of total star formation rate for mass of the cluster. So in general, cluster were more star forming, and also the fraction of star forming galaxies was higher at high redshift than in the local universe. We also know that the morphologies change, so there is an overall variation, so galaxies were more star forming. However, we also have signature that clusters were already able to quench star formation. Here there is the quench fraction efficiency. Here you have the formula. So in general, this quantity tells us how many galaxies are quenched due to the environment with respect to the fraction of quenched galaxies in the field at the same epoch. And first of all, we see that this number is larger than 0. So we have already an excess of quenched galaxies in clusters than in the field. And we also see that we have an increase with stellar mass. So more massive galaxies were already more quenched at high redshift. Another thing that we can look at is the star formation histories. So here there is a star formation rate density for cluster galaxies in red and for field galaxies in black. Just forget the other lines that are some finer definition of the environment. And here we reconstructed the star formation rate density based on the spectra that we observe for galaxies in the local universe. And then, thanks to the reconstruction, we managed to understand how much star formation there were at different epochs for these galaxies. In the top panel, we have the absolute numbers. In the lower panel, we just normalize the lines to the lowest redshift just to really see the slope. And we really see the cluster galaxies have a much steeper slope than field galaxies. So since the beginning, the star formation history of galaxies was different in cluster and in the field. And this in general is due to the fact that we had more star-forming galaxies now are quenched, but also that overall, the typical star formation rate is lower in clusters than in the field. So now the question is, how can we reconcile the fact that star formation histories were different from the beginning? And all the results that I've shown before, that we can detect environmental effects that act at the time of observations. These two things seem to be in contrast. A possible scenario is that actually we are looking at different families of galaxies in clusters. Bianca back in 2006 proposed that the passive cluster population actually is made up of two different populations. We have the quenched galaxies that are all those galaxies that infall into clusters at any epoch and quench because they enter this dense environment. And then, though, there are the primordial passive galaxies. These galaxies have been passive at least since redshift 2. They were in the highest density peak of the universe already at high redshift, and they've always been at the peak of the density during their life. So, in general, these two populations have a different proportion and so a different importance at the different epochs. At high redshift, the cluster passive population is dominated by the primordial population. At low redshift, quenched galaxies actually play the major role. This is just a possible scenario. Do we have any evidence for this? The answer is yes. We just have a couple of indirect evidence. Here, there is the size-mass relation of galaxies in clusters in the top, in the field in the bottom. Star-forming galaxies on the left, passive galaxies on the right. And this is done at redshift around 0.5. So, first of all, we see that there is not a huge difference between the size-mass relation in the different environments. But what is important is that in passive galaxies, we actually see two different slopes. Passive galaxies must come from the field star-forming population, at least the quenched ones. So what we can do is to measure at each stellar mass the difference between the size of the cluster passive galaxies to the size of the field star-forming galaxies. And this is shown here. Here we have the offset for the size of the star-forming galaxies in the field as a function of stellar mass. And here we color code the points based on the U-V color that can be used as a proxy of the age of the galaxy. And what we see is that massive galaxies are already very red and are here. And so these galaxies have been quenched forever. At low masses, we see two different trends. There are the galaxies that are smaller and are also a reddish color, so they have been quenched for a long time. But the galaxies that are quite big, they have size that are similar to the field star-forming population, actually are very young. These galaxies just entered the cluster, didn't have time to change the morphology, didn't have time to change anything, they just quenched. So they are really just recent infallers that change the star formation. So this is evidence of the fact that we have the primordial population, very massive, that is already in place, and this new accreted population. Another example can come from the morphology density relation. So we know since the 80s, Dressler showed us this morphology density relation that we recently revisited. So we have here on the left the morphology density relation. Red colors are elliptical galaxies, green S0 galaxies, and blue spiral galaxies. We really see the typical, what we all know. And on the right, we have the same relation as a function of distance. Elliptical galaxies have a strong dependence on the local density and no dependence on distance. Elliptical galaxies are most likely the descendants or are the primordial population. Their fraction always dependent on the local density. They've always been at the peak, at the density peak, so these are really galaxies that have been quenched forever. Instead, we can look at the late spiral galaxies and zero galaxies, and we can see some signature that actually these are the quenched population. Indeed, here we can just consider late type and S0 galaxies in 3 beams of cluster-centric distance. These 2 are the cluster cores. Here we have the cluster outskirts, and again, here is the distance. And we see that far from the cluster outskirts, there is a dependence on local density. Fine. In the cluster cores, we see that the dependence really washes out. We don't have clear trends anymore. So outside the clusters, local density play a role. When we get into the cluster, S0 get transforming for spiral because of the global environment. So we need a global environment to affect these morphologies. So these are more likely related to this new quench population. Do we have any direct evidence? Very little. One example is by measuring ages at redshift larger than 1. This has been done by Go Green, and we have the star formation histories of galaxies in the clusters and in the field as a function of stellar mass. And we see, overall, the cluster galaxies were already older, but just of 0.3 gigayears. This is not very strong result, but it's already a hint that cluster galaxies were already quenched much easily at high redshift and have been quenched for a longer time. And also, actually, low mass field galaxies have a more extended star formation histories, while cluster galaxies have shorter star formation history. So we need to go even at higher redshift. And the only example that now we have of a protocluster at high redshift, a redshift larger than 7, where we still don't know if we can see some signal of these 2 populations, has been observed in Able 27044 thanks to the GLASS ERS program. Here we detected 7 galaxies that actually are the same redshift, but when we look at the star formation histories of all these galaxies, on one side, we see that except for one case, star formation histories are very similar. These galaxies are already evolving in a similar way. But it's not shown in this plot. If we compare this with the field star formation histories, actually these are very similar. So at redshift 7, for now, we are not seeing any evidence for this primordial population being already in place. So I can just conclude. So I think I showed that clusters represent the most extreme environment in which galaxies reside, and galaxies are strongly affected by the cluster environment. We can have different physical mechanisms that remove the gas, but in general, RAM pressure stripping is the most important mechanism in the local universe. Spatially resolved data are really important to really characterize the mechanisms, see what's the effect of this physical process on the spatially resolved processes, spatially resolved properties. We can, the hypothesis is that cluster galaxies can be subdivided into 2 big families. We have the galaxies that have been quenched forever, the primordial population, and galaxies that just quench as they fall into the clusters. But unfortunately, we don't have enough data yet to really probe this scenario. So we really need to have larger cluster samples, especially at high redshift. Trying to characterize the population at redshift 2 and 3, it's really the key to understand the role of the environment in shaping galaxy properties. And I'm on time.
Thanks. We have time for some questions. All the way in the back.
Thanks, Benedetta, for the very nice talk. Regarding the last point, the high redshift, the redshift 7 cluster, do you think that the fact that we are not seeing a difference between the star formation history of the cluster galaxies and field galaxies can be due to the fact that maybe the galaxies are young and then our codes to estimate the star formation history are not like precise enough to see the difference, or it's physical?
Well, it could be, even though we ran, I think, different codes, different star formation histories codes, and they all gave the same result. But what I think more is just with 7 galaxies, it's very hard to say something. This is just the first hint. We really need to see with larger sample, because it's also, yeah, there are no clear comparisons, and I wouldn't get too much out of this.
What about the average age of the stellar population? It's similar, the same?
It's similar. At that point, but again, yes, just 7 galaxies, so yeah, but it's similar.
Wonderful talk, Benedetta. On your last point, you said more data, your conclusions, more data.
Yeah.
What kind of data would you really like to have?
Well, we need data on protoclusters. For now, the data that are available for protocluster are very sparse. Protoclusters are selected in different ways. There is not a big sample of an homogeneous sample that allow us to get statistical analysis. All the results are, many times they are contradictory. There are some results that show an enhancement of quench fraction, some results that show more star-forming galaxies, but we don't have a common ground yet. So we should have, like a Go Green, an E-disk, a wing sample at redshift between 2 and 3.
When you show that the elliptical galaxies trace the local densities instead of distance to BCG in the cluster, can I interpret it as those elliptical galaxies, they trace local substructures of clusters? Basically, they are BCGs of smaller clusters infalling into the system some time ago.
Say it again, sorry.
Can I interpret the elliptical galaxies in the cluster that are correlated with local density as BCGs of groups that infalled into this cluster some time ago, basically substructures?
Well, I think that there are too many to all be a BCG of their own group. The thing is that massive clusters today were already at the peak of density at high redshift. They've always been the peak, and so those galaxies have been in the highest density at all epochs, even though they weren't the BCG of their own group.
All right, great. So our final speaker before coffee is Greg Rudnick, and he's going to be talking to us about cluster galaxy quenching from Go Green.
Thanks so much. Like Stephanie said, my name is Gregory Rudnick. I'm a professor at the University of Kansas. And I wanted to thank the organizers for this great meeting. I'm learning a lot, and I have been eating way too much Italian food, but with great company, people I've read about for a long time who I haven't met, so it's been fantastic. Thank you so much. So today I'm going to be talking about cluster quenching of galaxies at high redshift from the Go Green survey. Benedetta gave a fantastic introduction and review of this entire field and included some of the Go Green highlights. I'll be talking about some other things as well. So we've been seeing in this conference the fantastic detailed studies of galaxies at many different redshifts, mostly at low redshifts. And so you can ask the question, why should you even study cluster galaxies at z greater than 1 when we have such a wealth of data locally? And for example, we'll never have the hope of getting lots of H1 and cluster galaxies at z greater than 1. The reason is basically because cluster galaxies in the local universe are old. Right? And so if you look at this really nice plot from Smith et al. 2011, where they do stellar ages as a function of projected radius and stellar mass in the coma cluster, you find that for low mass galaxies, things on the outskirts of the cluster are younger, things at the center of the cluster are older, and if you go to high stellar masses where everything's basically quenched, even there you find that these galaxies in the center of the cluster have very old ages, and even towards the outskirts of the clusters, their last epoch of star formation was something around Z of 1 or higher. So if you want to find out what quenched the passive galaxies in clusters today at any mass higher than around 10 to the 10, you need to go to Z greater than 1 to find that out. Now you can go a little bit higher in redshift just to see how things change, to Z of 0.6 or so. This is from a paper by Remco Vandenberg using Planck clusters, where he measured the mass function in Planck clusters and compared them to those in the field. And what he found was that the passive galaxy mass functions looked significantly different from each other. There was a definite difference in the faint end slope of the low mass functions that showed a big enhancement for low mass galaxies. At high masses, the galaxies were all quenched. But you have to ask the question, these are all galaxies, these faint low mass galaxies here, these low mass quenched galaxies here, that were already quenched at Z of 0.6. So what caused this quenching? That forces us to go to even higher redshift, and that introduces me to these three science questions I want to touch on in this talk. The first one is, what is the origin of these galaxies that were passive even as far back of kind of Z of 0.6, 0.7, 0.8? What environmental processes are acting at Z greater than 1, and with what efficiency? And then, indeed, is environmental quenching even important at high redshift? We talked about these primordial galaxies that Bianca first did in this paper in 2006 in eDiscs. What could have caused these galaxies to quench? And so I'm going to be talking about this in the context of GoGreen, Gemini Observations of Galaxies in Rich Early Environments. This is the premier spectroscopic survey of high Z clusters. It was performed on Gemini North and Gemini South. I want to recognize that Gemini North is on Mauna Kea, which has very significant cultural relevance to the Hawaiian people, and we're really fortunate and privileged and honored to be able to conduct our observations from there. So GoGreen has a huge team. Michael Ballo is the PI of GoGreen. Jillian Wilson, myself, Adam Muslim are on the management team. There are many people in this audience who are on this list, and everybody who's blue on this list are people who were students or postdocs at the time that they did their work. And there was a lot of really distributed work across this whole collaboration. The purpose of GoGreen was that we wanted to pick systems at higher redshift, Z greater than 1, that were the likely progenitors of Virgo to Coma mass clusters today. The backbone of this was a 530-hour large and long program conducted at the Gemini Observatory with GMOS. It targeted 21 systems from a redshift of 1 to 1.5 at, I would say, cosmic mid-afternoon. So these are right after cosmic noon, when the star formation rate density was starting to decline. We picked our clusters right over there, and we had clusters and groups, so a total of 21 systems over that redshift, spanning a large range in halo mass. As one example of the GoGreen data, this is one of our clusters, admittedly one of the most massive ones, SPT 0546. Some of these were SPT selected, some of these were optical and infrared selected. And you can clearly see an overdensity of red galaxies in this color image, but the spectroscopy is absolutely invaluable, because if you look at the distribution of non-members and members, you really find that even in the cluster core, there are lots of galaxies that are not spectroscopic members. So if you want to get high fidelity measurements of these cluster environments, photometry and photometric redshifts are good, but you need lots of spectroscopy to really be able to say something quantitatively about the membership. But it goes way beyond that. We did 15-hour masks on our spectra, so these are ultra-deep spectra that lets us detect redshifts for passive galaxies all the way down to 10 to the 10.3 solar masses, and we have this huge range of photometric data for our galaxies. That's one of our example spectra, so we can measure spectral features in these galaxies and really start understanding what happens in the quenching process. The data were released in 2020. That's 1 year after we finished observations, so we're kind of very proud of our record of getting things out to the public. And there's images from both the ground and HST, high fidelity catalogs, and then all of our spectra at this data release site right there. We also have Jupyter notebooks that let you understand how to read in the data, how to analyze the data, and how to do science with the data. So this is what the GoGreen spectral sample looks like. Every line in this plot is a GoGreen spectrum. It's the same plot I showed in the very first slide, except with the color scale reversed. The dark things are emission lines, so you can see O2 marching up for all of our galaxies here. This fuzz is really the night sky emission that we were able to get around by using the exquisitely sensitive Hamamatsu detectors on GMOS. You can see what's more important even than O2, because I hate to say it, but O2 is easy, right? We've been measuring O2 out to Z of 1.5 for a while, is all of these absorption lines that you see in these spectra. So we're able to get redshifts for passive galaxies using Balmer lines, calcium, H, and K. You can see magnesium-2 in some of our galaxies and O3. And you can see the effects of environmental quenching already on this plot, which always blows me away. If you look here, for example, you see all these O2 spectra, and as soon as you go into the redshift regime spanned by these clusters, the fraction of things with O2 emission drops. So that's kind of it. We know that clusters have a high quench fraction. I'm going to talk about this, but the main result is right there. So we did lots of investigations. Benedetta already talked about this one investigation from Lindsay Old that showed that star formation in the go-green clusters is suppressed. What this means is that galaxies are already being modified by the environment as far back as Z of 1. We see the star formation rates being suppressed, and we've seen that in other results at lower redshift. We then tried to take galaxies and select transition galaxies, galaxies that have a fast quenching time scale. They move through a very specific region of color space. Sirio was the first one to point this out in the paper, and then we kind of did it as a function of galaxy age in this paper by Tracy Webb. And if you select galaxies in that region of color space, which we call blue quiescent galaxies, you find that there is an excess of those galaxies transforming compared to the field, right? So galaxies are being transformed in a rather quick manner from star forming to passive. It happens mostly at low masses, and this is very similar to the kinds of things we see at low redshift. So until now, you could kind of paint a picture that things don't look very different from low redshift, that the way quenching proceeds in these clusters is somewhat similar to the things we've seen in WINGS and E-disks and G-class. So Remco Vandenberg did mass functions in a paper that I was on in 2020, and there he found something quite surprising. So these are the total mass functions, the mass functions of star-forming galaxies, of passive galaxies, and then we show the quench fractions as a function of mass. And what you can see is that the passive galaxy mass functions have the exact same shape in these two environments. The normalizations are different, but their shapes are indistinguishable, also for the star-forming galaxies. This looks very different than things just even down at 0.7, Z of 0.7 or 0.8. There you find that the passive galaxy mass functions look very different, but here they're identical. At any mass that you go to, be it 10 to the 11 or 10 to the 10.3, the go-green clusters have a higher fraction of quenched galaxies than the field. So something has to be happening that is really enhancing quenching in these cluster environments, at least in the past, because these are already quenched galaxies, but does it in a way that preserves the shape of the mass function. And this is very different from anything that we've seen at Z of 0. So we have to ask ourselves, what kind of drives this? Is this a sign of some new kind of quenching process? Is environmental quenching at Z greater than this? Something that doesn't happen? Is this some enhanced intrinsic quenching? So we've done lots of work to try and understand this. Benedetta also showed this plot from Christy Webb that shows the age distribution of passive galaxies using cross-spectrum modeling of the spectra and photometry. And as Benedetta pointed out, we find that the cluster galaxies are slightly older in their ages than the field galaxies. This is actually not what you'd expect from kind of a classic quenching upon infall scenario. If I had two galaxies of identical mass and one was passive because of intrinsic quenching and one quenched on infall at later times, it should be younger, not older, right? So this also points to something different than what we've been thinking about for classic environmental quenching. We also wanted to look at how galaxies quenched regarding where they were in the cluster. So did galaxies that are quenched reside in the cluster? Were they quenched in the cluster, or did they quench in the outskirts? So this paper by Stephanie Werner, who was a student of Nina Hatch at Nottingham and is now at Durham as a postdoc, looked at the regions around the go-green clusters and wanted to see whether or not the quench fraction there was the same as in the clusters or same as the field, and she actually found that the quench fraction in the infall regions of the cluster was intermediate between that in the cluster and outside the cluster. And using that, she was able to find out, or able to derive, what fraction of galaxies at every mass quenched after they infell into the cluster or before they fall into the cluster. At low masses, it's about 50-50. Half the galaxies quenched by falling into the cluster. But if you go to the high masses, almost all the quenched galaxies that you need to have quenched in the clusters were already quenched outside the clusters, right? So what we call pre-processing, which has only been mentioned like a handful of times in this conference, which is very different than what would have happened 10 years ago. It would have been in every other talk. Pre-processing of these systems actually seems to be dominating how the massive galaxies are quenched. And so this is weird because you've got this interplay of processes. You've got pre-processing dominating in high masses, maybe infall dominated quenching at low masses, and yet the mass function shapes are the exact same in the field and the cluster. So it's quite a mystery. We tried to tie this all together in this paper led by Tay Baxter, who was a grad student of Mike Cooper's at UC Irvine and is now a NASA postdoctoral fellow at Goddard. He used illustrious TNG to measure the infall histories of galaxies of different stellar mass, started with field quenched fractions at higher redshift, and then asked what the quenching time scale as a function of mass would have to be to reproduce the quenched fractions as a function of mass in the go-green cluster. So we let galaxies fall in, given the infall histories from the simulations, and then asked what time scale they have to quench on. And what he found in his first paper was that there's a mass-dependent quenching time scale. The massive galaxies, and this is now really like environmental quenching. They crossed R200 and they quench. The quenching time scale is shorter for the most massive galaxies and longer for the low-mass galaxies. And even if you account for this pre-processing, you still get that red line, which shows that mass-dependent quenching, right? So the quenching time scale is mass-dependent, which is also somewhat different from what we infer at lower redshift. But if you try and interpret this and you use models of gas consumption from Gergel-Popping's work, then what you find is that this time dependence of the quenching time scale is very similar to what you'd expect from just gas consumption. So starvation, which is what Benedetta said was one of the important mechanisms. We've all known this for a while. If you then ask how this evolves with time, you find that the quenching time scale evolves down to lower redshift exactly as you'd expect for that gas consumption over time. And if you just take the quenching time scales from go-green and evolve them by the dynamical time scale, they also match perfectly these expectations. We then compared the go-green quench fractions to hydrodynamic models, where we tried to really consistently select passive and star-forming galaxies between the two samples. This is a paper by Egidius Koukstis, who is a grad student at Liverpool. And for central galaxies, as we kind of know, the quench fractions from things like Eagle and TNG 300 match the observations pretty well. When you get to satellite galaxies at these redshifts, you know, the overall normalization of the data in the models at these masses doesn't look too bad, but the actual sense of where the models and the data go is totally different. The data have quench fractions that consistently decrease towards lower masses, and the models have quench fractions that consistently increase or are flat to higher masses. So I don't know what this means. There was some thoughts about it in the paper, but we don't yet quite understand where this difference in the quenching slope is and what the models have to do to get that better. So one of the last questions is what quenched those first cluster galaxies? I'm not going to answer that question here. I'm just going to give two hints that we'll hear about in future talks. One, as Benedetta mentioned, is going to protoclusters. We need to understand what the state of galaxies were in protoclusters, and we have evidence that some protoclusters were highly quenched. So McConaughey 22, that Gillian Wilson will talk about, find spectroscopically confirmed quenched galaxies in protocluster at Z of 3. It's also possible that this has absolutely nothing to do with environmental quenching. And Lamim Ahad will show in her talk that, in fact, it could just be a biased halo mass function in the infall regions of clusters, such that cluster galaxies have a higher halo mass, so the fixed stellar mass. And so it's just some kind of enhanced intrinsic quenching from a biased halo mass function. So how are we going to find out what's actually going on? The key is not just doing quenched fractions. We've done that. We've done it a lot. We're kind of tired of doing it. We've learned what we can from those. We need to understand how the baryon cycle is disrupted. We need to understand the interplay between star formation rates, metallicity, and gas. Taddy talked about this very nice in his talk. We need a systematic probe of the baryon cycle. Now, we're doing this. We're getting star formation rates and stellar masses from a MOSFIRE and Gemini program. But what we really need is a systematic measure of the cold gas using ALMA. And it's something we're trying to get, hint, hint. If you want to think of that as a good thing, then remember that if you're on the TAC. And we also need to go to protoclusters. So we also are trying to follow up and get systematic coverage of ALMA data in protoclusters. So here are my takeaways. Systematic surveys of dense environments are powerful. Environmental quenching is indeed in full swing at Z of 1, but it acts differently than at Z less than 1. Understanding quenching requires understanding the baryon cycle, and we need to look for evidence of quiescent galaxies in dense environments at high redshift. Thank you.
Questions?
What are the perspectives about getting information on the hot gas, which seems quite important?
You mean the hot gas in the clusters?
Yeah.
So it's really hard. eROSITA detects 3 of these clusters in Go Green, the 3 most massive ones, which were SPT detected, which we already knew what the hot gas was doing. Getting the X-ray on the other clusters, even though they're massive, is very difficult. The sensitivity of the X-ray telescopes is going down and down and down. So you're talking really large programs. So we haven't really pursued this very actively just because it would require incredibly long integration times. It's something we'd like to do, though.
Do you have any indication that they look, that the ones that are detected, they are similar to local clusters? Or?
I mean, so we haven't analyzed the eROSITA data yet. We've just have the published SPT data, and I don't actually know if there's been an analysis yet of what we expect for the ICM conditions given those data. But they're among the most massive clusters in all of eROSITA. That's all I can say.
Thank you. You showed the similarity of mass function for star-forming and passive galaxies in your clusters. So this brings me my memory of the mass quenching paper Penn et al. 2010, where they showed a similar thing, and they argued that it is a strong implication for the quenching rate to be exactly proportional to the star formation rate. Could you comment on that?
So this is actually very different than the Peng expectations, because the Peng expectations claimed that the quenching efficiency for environment was independent of stellar mass, but because of the relative shape of the stellar mass functions, you end up resulting in this very steep mass function for the passive galaxies. So in fact, going back to my intro right here, this is what you'd expect from the Peng result at lower redshift. You'd expect an enhanced faint end because you have many star-forming galaxies. You're quenching star-forming galaxies equally at all masses, and because you have many more star-forming galaxies, you actually boost the low mass N. We don't actually see that in Go Green. We see exactly the same shapes, and we think that's being driven by this mass-dependent quenching timescale, which wasn't in those earlier models.
Good. I can ask a question. Okay, well, I have lots of questions, but my first question will be, I have in my head that it is incredibly difficult to identify protoclusters as you move to higher Z. So one of your goals is looking at clusters at high redshift. How possible is that to get kind of the numbers we need?
So we're trying, right now, because we have what we have, we're trying to follow up protoclusters that currently exist. But as Benedetta said, there is a wide heterogeneity in how these are selected. I think Euclid and then later Roman will very much help us in getting systematic samples of protoclusters. Nina Hatch's student Harry Goley has a paper about selecting overdensities using IRAC. And so there are ideas to get big homogeneous samples. It's not detecting the candidates that's the hard part. It's getting the spectroscopic follow-up, right? If you want to do this with Keck, you need a really large program with Keck to confirm these. So maybe Euclid will be able to help us with this, maybe MOONS, but I think what we need is dedicated large spectroscopic programs. I know MOONS is going to be doing this as part of their GTO program, but that's kind of where we're holding back right now, is waiting for that. So I actually wrote a white paper for Roman that was talking about how we need to do really deep, large area Roman spectroscopic surveys to find protoclusters, hit one of the deep drilling fields, go like 30,000 seconds, and then you can actually get down to these kind of stellar masses and find protoclusters with Raman spectroscopy. So that, I think, would be a really great way to do it, because it'll go deeper than Euclid.
Well, I'll ask you my other questions over coffee because it's time for coffee. But thank you.
Just very, very quickly. Sorry. The person that left this bag that is coming soon at the restaurant, yes, please come to me. Your bag is safe, but come to me and we'll find a way to get it here.